Hello everyone. We'll continue with lecture 2. I hope you can hear me. And if you cannot hear me, then let me know. So we were here last time, and what we said is that optimization problem appears in a lot of problem. Most of the problem actually boils down to optimization problem, and we are going through some examples. We have seen some examples that we may have seen before, and we were here last time where we are trying to formulate a problem from, let us say, data science as an optimization problem, and let us see what is involved here. So remember, we were talking about temperature data of a city in a day, and the samples that we have are these. At 9 the temperature is this, at 11 the temperature is 30 degrees Celsius, and so on. So this is the data that is given to us for one day. Okay, we could have had this for even multiple days also. And the question is, so we want to do the prediction of the temperature at 14:30. Okay, so it's like 2:30 p.m. We want to do the prediction, and the question is, if this problem is a optimization problem, then what are the objective functions and constraints, and what is the overall model that we are looking for? Okay, so the data that we have, we can rescale the time. Hello. 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 You can turn off your microphone. When you want to ask question, then you turn on. Okay, but turn off your microphone, and you can raise hand also. Okay, there is a raise hand feature. Okay. So we can rescale. Okay, the time. Okay, we can rescale and we can reinterpret later on also. Okay, so for in the rescale time, the question that what is the temperature in 14:30 is the same thing as saying what is the temperature at in this case, like it's like a 4:30 in this case, right? Rescaling is just to draw the graph from starting from 0. Okay, it doesn't really matter. You could have started from 9 also. Okay, so I want to start from 0. Okay, and so at 0, 0, we are given so let us say the marking that we have, okay, are like this. Okay, so let us say it goes via, let us say 10, 10. Okay, so 10, 20, 30, 40. Okay, this way the temperature, so this is the temperature scale, and this is the time scale, and and the timing we can have for example here, these are the times we have. Okay, so let us say this is, so this is the 2, this is 4, this is 6, this is 8, this is 12, and then we plot the values, right? So at 0 it was already like 9, so it's somewhere here. Okay, oops, this, okay, so somewhere here. Okay, and at 2 we have 30, so it's somewhere here, and at 4 we have 34, so it's somewhere here. At 6 we have 33. Okay, so it's slightly below, and then we have at 8 we have 21, so it's somewhere here, and then so on. Okay, so this is the pattern we want to understand, and maybe it's looking something like this. Okay, so your goal is to come up with these predictors. So goal is to find this curve, because once this curve is known, whatever value someone asks you to give, for instance here, then you can just project it upwards, and then you can say that this is the temperature for that. Okay, so this is how we can do. So what we are asking for is how to find this function f. Okay, So what happens usually in this type of problem? Okay, so this is like a very simplest data science problem you can think of. It's called fitting a curve problem. Okay, so given data sets are there, and then you're trying to fit a curve. What you do usually is that you actually start with a template. Okay, template of the function that you want to fit. So that is that template you already fix in advance. Okay, so that is something you fix in advance. For instance, I could have said maybe I want to fit a line. Okay, or maybe I want to fit a quadratic. Okay, or maybe I want to fit a cubic. So which of these you want to choose? It's a choice that you make in the beginning. Obviously, higher order means that your approximation will be close to the true pattern. Okay. For instance, if I want to fit this data with a line, then I will fit something like this, so that the distance from the data points is closest. But I have big error here because some points are here and then I have a lot of error here, right? If I use a quadratic, then my curve can bend. Okay, so there is more flexibility. I can use cubic, then my curve can bend more. Okay, so then there is a more flexibility to fit the data. Okay, so this is the very basic thing. So the initial intuition that we have is that first of all, actually you have to fix the data, the model that, or the function that you want to fit. Okay, so if it is a line, then you take the equation of the line, and if it is a quadratic, then you take the equation of the quadratic, and so on. Okay, so equation of the line we all know is written by ax plus b form, right? So this gives us equation line, and then if we were to use the quadratic, then we will use ax square plus bx plus c. Okay, and then we can continue this with the cubic and so on. Okay, so this is so the template is something we have to choose in advance. Okay, so in this case, let us say that I want to choose the template. Okay, so let me do it here. So let us say I want to choose the template of quadratic. Okay, so the first step is like choose template function. Okay, and this is what happens in throughout all the data science actually. Even if you want to use neural network, the template is something you agree in advance. Okay, I will discuss all this in detail later on. If you don't, neural network is nothing but just complicated function, as I said before. But the template, the initial template is fixed. Okay, you start with the fix. What is changing are the parameter. Okay, so let's see what. So so choose a template function. So let us say I choose the quadratic. Okay, so choose quadratic. Choose quadratic function. So the template function that I want to fit in my data is ax plus b. Okay, and I know that the parameters of my model, okay, that needs to be found out. Is it for a line? What are the parameters involved? I mean, okay, sorry, I'm saying quadratic, so let me do with the quadratic plus bx plus c. Okay, so so the question is, what are the parameters of my model, right? So parameters. So parameters here is what? Okay, so that's the question we are asking. Parameter is what in this case? So the parameters on a quadratic are indeed a, b, and c. Okay, these are because once I know this, give you these a, b, c, you know what is the function we are talking about, right? So the parameter is something we need to identify. The template is that it's a quadratic function, so that is already you fixed it. Okay, in advance you could have fixed it with cubic to start with, but you allow these parameters A, B, C to change depending on how the data has to be you want to fit. These parameters will decide how to correctly fit the data, how to move the curve, and so on, right? So these are the parameters that we need to estimate. Okay, so what do we do here? And remember that the data is given to you. Data is given to you in the tabular form. And the question is, how do you find a pattern in the data? And finding a pattern in the data is like finding the function. Okay, finding the function. And once the function is learned, as I said, you can find intermediate values after that. Okay, and that will form the prediction part. But the initial part is how to train our model, right? So the training a model is like fitting these template function that we are talking about with the data. So that's the training part. Once we have found that, after that some new data will come, which in this case is predict the temperature at 1430, and then that will be the prediction. So how well we have trained, how well we have come up, how well we have optimized the parameters of our model. In this case, it's a quadratic model that will determine how well we do during the test. Okay, so this is the tabular data we are given, and we have to make use of this tabular data to estimate the parameters of our model. Okay, so these are the parameters of our model. So what we are given are the samples we are given. Okay, so let's say we work with the scale time. Okay, as I said, scaling is just a simple thing here, just a shifting towards 0, right? So so we are supposed to estimate the parameters. So what we are given is the data. So according to the data, we have to tune on these parameters. So what I know is that if it happens to be a good model, it should fit the data that I'm given. In other words, if I put those X values, then it should produce those output values, which is the temperature. Okay, and input in our case is the time. So what we have is like for those, so at time t equals to so in this case our time is like x here. Okay, so at x is 0.00. Okay, this is the scale time. Our output that we have is, we will check here, it's 15. Okay, this is 15. So this is what our function should do. So f at 0, 0, which is a times 0 squared plus b times 0 plus c, and that should be equal to 15. Okay, similarly we do the other times. So other time is 2. So f at 2 is equal to a at 2 square plus b at 2 plus c, and that temperature was 30. Okay, so similarly we do this. Okay, so now so what we are trying to do by putting an equality here, we are trying to say that, well, this is my requirement. If this is what I really want from my model is a quadratic model, and then at these sample points it should produce the output given in the data. Okay, so output is like a level here. So and using these equations now, we have to solve for this, right? So now the question is like, what is this? So is in the mathematical form, how does this look like, right? So so how, I mean, and also like, where is the optimization coming here in picture, right? So what we know from here is, I can continue here. So what we know from here is is the following. So let us say these are anyway some numbers, right? So here like 0.0 is some number, and this is some number, and this is c times 1 we can think of, and this is some number. Here also c times 1 is some number. Okay, so and what is not known here is ABC. Okay, So what I can write this is as follows. So I can write this as, so as let us say C11A plus C12B plus C13, and then it's 1, right? So it's 1 here, and that is 15. So C11 in this case is like 0.0 square, C12 is 0.0, and C13, oh sorry. So this is like C here, okay, and C13 is 1, okay, so C13 is 1. Similarly, I can do C21A plus C22B plus C23C is 30. So what you get in the end is, and C1's Cij's are known. Okay, these are the data knowns, and A, B, C are unknown. Okay, unknown. So this is nothing but a set of linear systems that we want to solve, right? This is a set of linear systems that we want to solve, but there is a problem. Okay, the problem is, although I am asking my model to get this output, but there is no guarantee that these equalities will be met, because let us go back and see here. Let us say that you started with a template which is a line. Now you know that your data points are here. Okay, you know that your data points are here, 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 and so on. So surely your line cannot satisfy the equality of going through all the points. Okay, so that is out of question. So similarly, one can say in the cubic case, let us say some data points were here, but some data points were here. Okay, let us forget this example, but let us assume some other example was there. So a quadratic cannot really ensure to go through, because quadratic cannot do like this and then it bends like this. Quadratic doesn't bend 2 times. Okay, quadratic function always bends 1 times, either this, either this. It can shift left, right, up, down, that is different. But if your data has this pattern, then quadratic will try to fit it something like this, okay, or something like this. So that's the problem. So what you may be asking for here in the equality, it may be too harsh. But on the other hand, you don't want to change your model because you want to go with the cheap model. Cheap in the sense like model that does not have too much parameter in them. So cubic is a very cheap one. It has just 3 parameters to estimate. One could have gone on with 100 dimensional, 100 order polynomial and so on. But then the number of vector length is increasing. So you have 100 parameters to estimate. You know, the complexity is in. So what you are saying here is that, look, I don't want to build a very complicated model. I want to build a good enough, small enough model, and which is a quadratic in this case. So quadratic has 3 parameters. I'm happy with that. But still, I want it to fit it well. Okay, it may not pass through all the points because it may not bend 2 times, but it can still make the error very less. Okay, so so in this case, asking for equality is a bit too much. So what you will ask for is approximation here. Okay, so what you will ask for is approximation. Okay. So let me, so what we can hope for is like this: C11A plus C12B plus C13C, and this happens to be some output, let us say B1, which was the temperature. Okay, so we are writing it symbolically now. C21A plus C22B plus C23C is B2, and this way it goes on. Okay, and eventually we have, let us say there were n data points. So we have n1a plus cn2b plus, oh, okay, I'm sorry. Yeah, that's fine. So cn3c is bn. Okay. So this is what we have. But what I said before is that this equality is not really guaranteed. Okay, this equality is not really guaranteed. So what you can best ask for is just they're close enough. Okay, so they are like they are approximately close, approximately equal. Okay, approximately equal or like as close as possible. But not in many cases you cannot say equality. Okay, because you are modeling high dimensional problem with a small model. Okay, so you may the best you can ask for is the equality. Okay, so if I can write this in the matrix form, you can immediately see that I can write this as C times X is equal to B, where C is the matrix. I am planning to do a review of vector also. So in case you don't have enough, then you have some time to revise. Okay. Okay. I don't know why it's overlapping too much. So Cn1, Cn2, and Cn3. Okay. So this is the matrix C. Okay. So there is nothing here, and X here is A, B, C. So these are the unknowns in my model. Oh, okay. I should not use the same B, right? Okay. So this is like, let us say Z. Okay. So Z is B1, B2, B3. So, and also, as I said, equality is not really possible. So what we are asking for is Cx approximately equals to Z. Okay. So by approximation, we mean like we want these guys to be as close as possible. So this is same thing as saying that the norm distance of is the same thing as saying that the norm distance of Cx from Z is minimized, right? Over all possible X, the parameters in your model are all hidden here. So you have the liberty to change the parameters in your model. And what you are asking for is this. So this is where you see the optimization problem, optimization model. So yes.
What is order of that norm?
What is order of that? You can choose some norm, let us say 2 norm.
Okay, it's
okay. The usual Euclidean norm you can choose, and yeah, so if you want to make it like differentiable and so on, I will come back to this a bit later. Okay, you want to make this differentiable and so on, then you can also square it. Okay, because in the usual 2 norm, I will actually still I'm going through a very a top level review. I haven't defined norms and everything, but anyhow, like you pick any norm. Okay, let us say 2 norm, and you could have squared it to make it differentiable. Okay, I will. Maybe I'm jumping the gun here, like why should I square and so on. But okay, let us leave that later on. Yeah, we will do it later. But let us say some norm that quantifies the distance of Cx from Z. Okay. So from here itself, we know the optimization problem. So minimize over X, where X were those parameters of your cubic equations. Okay, so minimize over X. What do you minimize? This is the Cx minus Z. Okay, so you can only hope of minimization because your model may not exactly fit. So what you are asking for is the best possible distance, as close as possible to the level, which is in our case is the Z. And you minimize this. Okay, and there is no restriction here in X. So this is an unconstrained problem. So you are allowed to choose any arbitrary vector from the Rn. Okay. Okay, because A and B and C are arbitrary, and cubic equation can take any arbitrary values, unconstrained. Obviously, like infinity, all those values will not make sense, but those we call it unconstrained. Okay, infinity is really not in our, I mean, that is not even considered a real number, right? So this is what we have. And again, you saw a data science problem reduced to a problem of optimization problem. Okay, and what will be the result of this model? From here, what you are supposed to get is the X. Okay, so is the X that you are supposed to get. Let us say that is X star is the optimal. So this optimal A star, B star, and C star. And from here, now it becomes your prediction function once you substitute A by A star X plus B star a star x square plus b star x plus c star. Now this becomes after training, and this is the training part that is happening here, which is to solve the optimization problem. So training part of a data science problem is always solve the optimization problem. Okay, in any data science problem, when they talk about training, they talk about solving the optimization problem. Okay, that is where the model is learning, right? And model is learning via some optimization method. Okay. So once you have learned the optimal parameter of your model, you plug in your template, and then it becomes a predictor. Now it became a predictor function. Okay. So now someone gives you some temperature, let us say 2:30 p.m. You plug in there, and optimal thing are known. I mean this you have found an optimal graph. So now it will do a good enough prediction. So at 2:30 it will do a good enough prediction because your model has learned very nicely. Okay, so it may not be perfect as I am saying, but given the model size you have, which is quadratic, it is the best you found. Okay, it is the best because you have solved this optimization problem. Assuming that you have solved this optimization problem precisely, this is the best model you have found. For the given model, this is the best parameter you have found. Okay, one could have asked, like, I want even a better predictor. Then your only hope is to now go for cubic. Okay, so then the length of your model, size of your model is increasing. In cubic now the parameter will be 4, A, B, C, D. Cubic equation will have A, B, C, D. So parameter size is increasing. So these are the things you decide. Okay, and another problem is for a bigger model, as I said, as the n increases in the first class, I said optimization problem has a lot of load. Because the vectors are big, so the solver will be slow to solve. If the problem size is increasing, as your model parameters are increasing, the optimizer will be slow. So are you willing to wait for 4 weeks to train and then you build the predictor? So sometimes there are scenarios where you have to decide whether to go for higher parameter model or settle with small, because the prediction you believe is still good enough for what you desire. Okay. So this is a very simplest data science model you can think of. I have explained the basic things in data science, which is training and testing. And where is optimization problem involved? If someone asks you, then you say that it's during the training part when we are learning the parameters of the model, then that is where the optimization problem is involved. We will see that we can choose more complicated models, which are so-called neural network models, and there the parameters also can explode depending on what is the size and the layer and whatever you want to choose. But at the end of the day, it will again be some optimization problem via which you will find the parameters of your model. So let us get into some other models. For instance, there is something called logistic regression. Okay, so this is used for classifying two different classes. Okay, for instance, some data is given for tumor, let us say. So some data is given for benign tumor data, and some data is there for malignant. Okay, and there is some level given to us that if it goes beyond 0.5, then it is classified as this. If it goes beyond this, it is classified as this. So your goal would be to find a function again. So in this case, it's a function. The only difference now of this function with the previous function, previous one is called regression problem. Okay, usual regression, and then this is called logistic regression. So the difference here is that I just want a function that can separate the data. Okay, I'm not asking for a function that goes closest to the data. Okay, that's the difference here. So regression, if you were a regression problem, then you will say how my template function passes closest to the data. But in logistic regression, you are asking how well a function can separate separate two classes. So this is another type of problem. We will get into this in more detail. As I said, it's still an overview, but it will turn out that it will turn out that it is again an optimization problem. And then here I have defined some loss function. Okay, so we will get into the detail of this. And the parameters are some theta parameter is involved here. Okay, so this is like some sigmoid is involved and so on. And I have built a loss function here with the given labels we have. Okay, so there are like samples, for example, this sample xi, and this is a malignant or benign. Okay, so this is benign. Okay, so let us say sample x1, sample x2. Then we are saying is it, so let us say sample x2 is here, sample x1 was here, sample x2 is malignant. Okay, so this way we have this. Okay, and what we are trying to fit in this case is the parametric model that we have chosen is this h theta of x, which is actually the sigmoid function here. Okay, and furthermore, what we have done is we have defined some loss function here. So this s theta x. So rather than doing the usual loss where we say s theta s how far it is from the given level, we are not using the 2norm. This is 2norm was one way of defining the loss, but for classification problem we used this kind of loss. Okay, we will get into this in more detail. So once you have defined the loss, instead of this 2norm, you are using the logistic loss. And indeed in the loss we have the label playing the role here. Okay, yi. So similarly in the previous case we had the label here, and from which we say how far we are from the actual. And this is another way of saying defining a loss. And we sum over all the samples. Okay, and and the sum over all the sample was implicit here also, because we wrote it in the matrix form in the previous case. So we wrote this in the matrix form, right? So when we take the norm, it will automatically take the sum over all the losses into account. Okay, so if you are not following fully, then don't worry, we will come back to this later on. So what I'm trying to say in this initial classes is that this is again a optimization problem, and what you're trying to do is minimize the loss. So in this case, the optimization problem is minimize j theta. Okay, minimize j theta, and theta is the parameter in your model. Okay, I have not explicitly told you what is that, but assume some model is there. Okay, it's like a sigmoid here, and this is what we have to do: minimize our loss function. So this is like loss or cost, or okay. So this is the loss function that you want to minimize, and what you are allowed to minimize over is theta. So I will vary over theta using some algorithm. I will try to solve this problem, and once I have solved this problem, I will get some optimal theta star, and for that theta star, I have the prediction function now. Now you can give me a new data, okay, of some patient, and then the output of this will tell me whether, so I will check for the output. So if the output is greater than 0.5, then I will say that okay, that patient X is malignant. Okay, so you see the general pattern that is evolving here in data sciences. What people do in data sciences, what people do is they start with a template function. Okay, in the previous case of the temperature data, we saw that we started with template. So it could be linear, it could be quadratic, it could be cubic, it could be 100 degree polynomial. But as you increase your model, you have to pay the price, because the training part will be slow because the vectors you are dealing with high dimensional. Okay, and here we saw the logistic regression case, which is a classification problem. And in this case, you are asking for a function that can clearly separate. By clearly, usually we will see all this in detail. We will also see SVM. So there, SVM is a rich source of optimization problem. Okay, so the point here is like, it's not just function we are asking for, but usually we are asking for a function that does a very wide separation. So the distance of this from this curve should be as far as possible. Okay, so SVMs and all those try to do that. Okay, because there may be outlier. Okay, there may be outlier, some outlier here. Okay, So we will see all those cases in detail. So we are also asking for a function that can clearly separate with a wide margin. Okay, so not just hitting, not just going very close here and then very close to some of these points and so on. So that's the idea behind all those all those SVM and so on. Okay, so there we will see that we want to widen the margin. Okay, we will come back to this. Don't worry about that. I go in a very very detailed way. Okay. So in this case, let us say we will find a predictor function, and then if it is greater than 0.5, then we classify it's malign, and otherwise if it's benign and so on. So this is again a optimization problem when you are doing the training part. Okay, when you are doing the testing, obviously no optimization is involved because you have already learned the parameter theta star and nothing to do. Okay, theta star is known, and then you just have to put the x and then get the output, and then depending on whatever threshold you have, you will define where it belongs to. And these are slightly more complicated models. These are neural networks, so-called neural network, and this is something I will discuss in detail later on. Today, again, it's an overview. Overview in the sense like we want to see where these optimization methods fit. Okay, and so I want to give you a general feeling of where are the problems, where are the applications where this fit. So one of the thing is neural networks. Okay, and it is called neural network because it's designed in a way that it looks similar to the way neurons are there in our brain, and there is networking among neurons and so on. And we believe that the processing happens layer by layer and so on. Okay, we don't exactly know how in more precise detail how our brain works. Our body is really complicated. But neural networks, the name neural comes from there. Okay. So so a neural network is like you are arranging a set of neurons. Okay, so you can think of some neuron here, some neuron here, some neuron here. Some input data comes. Okay, for instance, when you see something, then your eye is taking some data. Okay, whatever data it is, even the data that the way we perceive the data, it may not be even digital, right? In fact, our body works more in an analog way and so on, right? So even the data we see, we don't know exactly like how actually this data is fed, but assume that some data is there. In our case, it's like some real number, right? And then this data is processed by each neuron. Okay, each neurons. By processing here, in our case, since this is artificial neural network and not the biological neural network, so artificial neural network is nothing but some set of function evaluations here. So what we do is that we do this this kind of operation, which is nothing but a linear combination. And then after that, you do the activation. X was your input data, right? So X is your input data where X1 and X2 is there. It goes in, okay? And then you do W. W is the weight here, which is not known in our model. Okay, so the variables that is not known in our model are these W weights of your network. Okay, so in the logistic, the weight were theta. Okay, so sometimes the notations change. Okay, in even the previous regression problem, we took the weight as X. Okay, so it doesn't matter. Okay, we know what is to be found out. So these weights of your model are supposed to be found. Overall, if you see, this is nothing but some function. Okay, this is just a nested function because the output that you are getting here, okay, is now fed into the activation, second level activation. So this is like a nested function, right? So Y2 output that you are getting, Y21 is G2 of W2 of Y1. So Y1 was G of W1 and so on. Okay, so if you keep doing this again and again, so the outputs that you will get will be something like Gn of G1 of something like this. So it's a highly nested function. Okay, approximately, I'm not very precise here, but overall what we know is this is a very nested, okay, nested and nasty also actually. And so because it is nested. Okay, so this is the problem actually. The function itself is complicated. Earlier, we started with logistic is still simple. Okay, linear regression that we did was still simple. Okay, but these models are getting complicated. But on the other hand, if the function is complicated, then we are hoping that it will do miracles. Okay, and indeed it is doing miracles in these days. Okay, so this is one, and and these are like nested functions. So in this example, it will be 3 times nested. Okay, and where the activation functions are defined. You don't have to be very precise here. Okay, and here again, I will define some loss function here. Okay, so I will define a loss. Okay, and this loss define loss. Okay, this is the thing about all the data science things. You define some loss function, and the loss will be based on some FNN, which is the neural network you have, and the level that you have. Okay, so the output level is, let us say the the desired level is denoted by D. Okay, so let us say the sample was X and the level was D. Okay, typically people use Y, but here the Y is used inside intermediate output, so that's why I'm not using Y. So you define a loss based on this. Okay, and you minimize this. Minimize over what? Minimize over the weights, because weights are the something we don't know. That's the only thing we don't know. So minimize over the weight of these. And since weights, again, we allow any free weights, there is no restriction. So this is an unconstrained optimization problem. The unconstrained optimization problem, nonlinear, and so on. I will come back to linear, nonlinear, convex later on. So again, we model this problem as optimization problem. And the training part of the neural network is about minimizing the loss. Okay, minimizing the loss. And how to find the minimization of such problems is one of the half of the course is all about that. What are the solvers for the optimization problems? What are the good solvers? Like not just taking anything from anywhere, but to take it in a good decide it very well. Okay, okay, and this is another problem coming from machine learning model is so-called GAN. It's generative adversarial networks, and these are used to generate new images. Okay, so for instance, you train on some level data. So you already, let us say you train on a lot of cat data, and then later on you generate new cat images. Okay, so that's why the name is generative. So it can generate after, so for it can train on a lot of paintings, let us say natural paintings and natural scenic paintings, and after that it can start generating new paintings from there. Okay, so this is used in very artistic type of environment where you want to generate voice, you want to generate images. So people are doing all kind of things with this. Okay. Now here again, it's an optimization problem. It's a little bit more complicated. Already here you see the loss function is a bit complicated here. Okay, so there is a neural network involved with the generator. There is a neural network involved with the discriminator, and the losses are combined in certain way. I don't have context right now to give details of this, but we will look into this in detail later on. How this model was developed, like why we think of loss in the way it is. Okay, so that's the modeling part of this course, and and then what we want to do with this loss is minimize the errors that the generator is doing, and maximize the discriminator score. Okay, so there is more context here. I won't go into, but what we know from here is that this is an optimization problem, and it's a double optimization problem, simultaneous and double. Okay, simultaneous in the sense like you cannot say that I freeze D and then I max over G. Okay, and then I freeze G and then min over D. So that's iterative minimization, right? That's not the case here. It's simultaneous minimizations. Okay, so simultaneous minimizations is something what we are looking for. Okay, so graph could look something like this. and what you're looking for is something somewhere. Okay, that can also be formulated as a two-player game. Okay, we will see that in detail also, how a optimization problem is also actually one player is trying to maximize score, another player is trying to minimize the score. So you settle for some equivalence, like Nash equilibrium is there, where you settle for some place where it's beneficial for both. Okay, so we will see those in the solver part of this course, why min-max problems can be seen as a two-player game, and so on, and what are the ways to solve. So what are the ways to solve? Okay, so this is the first part of the course, where I wanted to give you an overview of what are some of the things that we want to cover, and today I will go to vectors and matrices review, just to make sure that you are in good touch, because those things are very basic and it's not needed not just in my course, it's needed in all other courses. So let me go to the other part. So I will open that. Okay, so I hope you can see. I have opened the review. So for some of you, it will be very basic, especially those students who have been who are undergrad in IIIT. So they have done linear algebra rather recently, 1 year ago. So for them, it will be rather basic, and something that they remember. For those of you who have done this, surely you have done this, but you may have forgotten a little bit. So I would like to do a quick review of this, and the class I lose for this, maybe I will do some extra class. But because without this review, I don't really want to start, because there will be discontinuity. So I want to do this review, and if I need additional class for my course, then I will take some additional class later on. So with that, as I said, some of you may find it very basic and easy, so I don't mind that. Okay, so if you think it's too easy. So let us start with the vectors. We will distinguish between, we will try to understand what is the meaning of point and vector. Okay, so we have been drawing elements of Rn as points in the line, plane, space, or whatever. For example, in this case, okay, so for example, in this case, this is 0.13, right? So this is 1 and this is 3. So that's how we represent the 0.13. A vector is an element of Rn drawn as an arrow. So we draw as an arrow because vector also has a direction. Okay, we think of an element of Rn as a vector, and we will usually write it vertically. So usually for us, the vector is a column vector. Okay, so point we can also represent this as a vector, but we will always assume that the tail of this point is at origin. Okay, so this is what we have done here. So you can give me any arbitrary point, and I see this as a vector by joining the tail. Okay, by joining the tail to this point. Okay, by joining the tail to this point. Okay, so for us, point and vector will be synonymous, but for the vector, we are assuming that the tail is at the origin. But we all know that this is same as this vector. If I translate this in a parallel way, these are same vectors, right? But in our case, we will assume all vectors are tailed at origin, because any vector it's not tailed at origin, we can always move and make it tail at origin. So in general, so why make this? So in general, we know that a vector need not start at origin. It can be located anywhere. For example, this is the same vector as this vector, right? What we know from our previous experience is that vectors are nothing but it should have the same magnitude and the same direction. That's correct. So this has the same magnitude, means length. This guy has the same magnitude, this guy has the same magnitude, and the directions of all three are same. So in that sense, these all three vectors are same. Okay, determined by its length and direction, but not by its location where it is in the space. Okay, so these arrows all represent the vector 1, 2. Okay. However, as I said in the previous slide, unless otherwise specified, we will assume vector starts at the origin. So we will always assume vector starts at the origin throughout this course. Obviously, we can add these two vectors, very preliminary stuff, A, B, C. So by default, all the vectors are column vector for us. Plus X, Y, Z is component wise addition, A plus X, B plus Y, C plus Z. We can multiply or scale a vector. So if we multiply by a real number, okay, so if we multiply it by a real number, which is C here, X, Y, Z, then it becomes C times X, C times Y, C times Z. Okay. We call C a scalar to distinguish it from a vector. Okay, so vector space always comes with a scalar field over which it is defined. Okay, so for example, in this case, when we say Rn, so Rn is a vector space defined over R. And so the scalars that we are allowed to choose from is the real number. Okay, but we could have constructed other vector spaces also, right? We could have chosen Cn. And the scalars that we are choose are now coming from complex number. So this is what we mean by scalar. Like what are the components of a vector that is allowed? So in this case, let us say it's real number. We will always stick with real number in this course. So scalar is just one number, okay, and one real number, and it multiplies to a vector. It multiplies component wise. So in this case, CV is called scalar multiple of V. Okay, so so for this is an example. I do a scalar multiplication of a vector 1, 2, 3 by -2, then I get -2, -4, -6. Okay, now vector addition and subtraction, and what is the geometry involved? So let us see the parallelogram law for vector addition. So geometrically, the sum of two vectors V and W is obtained as follows. Place the tail of W at the head of V, and then V plus W is the vector whose tail is the tail of V and whose head is the head of V. So to tell you, so let us say you want to add the vectors V plus W. So what you can do is that you can take one of the vectors like this, okay, and parallelly you move it, okay, you move this parallelly, and in such a way, of course, you are not allowed to change direction, right? So you move it parallelly so that it comes here. Okay, and you do it in a way that the tail of the vector lies at the head of the other one, and now you join this from the origin. So what is the end point you got? That point, okay, the vector joining the vector starting from the origin to that point is V plus W. Okay, this black line is V plus W. So that's what parallelogram law says. You could have also moved V parallelly and put it at the head of W, and that is also the same vector V plus W. So that's the vector addition rule. Okay, and vector subtraction. So vector subtraction is a special case of vector addition, because vector subtraction V minus W can be written as V plus minus W. Okay, so we could have written it as V plus minus W. Now you can apply the only thing now left is like you have to now do a negative of the other vector, and then you use the parallelogram law to do the subtraction, right? So now the natural question is, what is negative of W, right? So what is negative of W? For instance, here I have V and then I have W. Okay, so what is negative of W? Well, if I have a vector and then if I take a negative of that vector, where will it go, right? So if I take a negative of this, it will go like this way, right? It will go this way. Okay. So this is the negative. So now, now you have to add, right? So you have to add the negative of the W with V, right? So what will you do? So you will move this parallelly so that it hits the head of the W, right? And the line joining this is this guy, right? So this should be V minus W, according to the parallelogram law, right? But this vector is the same as moving it to this. This vector has been moved here just to just to show that that this is like this is also a one possibility, right? But since we are interested in vector starting from the origin, we would rather say that this is what we want. Okay, it doesn't matter because this vector and this vector is the same. As we know, location doesn't matter, length and this is same. Okay, you could also say like this is the same. I could have just joined this, right? Okay, but you know how to derive using addition only. You can derive. So so this is a vector subtraction. Okay, so scalar multiples of a vector, we have seen this. So scalar multiple, so these have the same direction but different length. So for instance, v is the vector. Then if I do scalar multiple is 2 times v, then it makes the vector 2 times more, right? So if this is the vector, this is the vector v here, and this is the 0 origin. Okay, so this is the origin here. If you do 2 times v, then it becomes this one. Okay, starting from origin, this becomes this one. So basically, 2 times means that I have scaled the vector 2 times the length. Minus half is like a 2-step thing. First thing is half of the vector. So half of the vector will be somewhere here. So this is half of v. And if I do minus, then it will just reverse the direction and it will be this minus of half of v. And then if we do 0 of v, then it will be a zero vector. It will just go at the origin, right? Okay. Yeah, just so. So what we know from here is the scalar multiples of v do form a line. It tells us how to stretch and compress, right? So compress will be when I multiply with a c that is between 0 and 1 interval. Then it will be a compression, or it will compress the vector. Okay, shorten the vector. And if it is otherwise, then it will always elongate, but the direction can change also. If it c becomes negative, then to go in other direction. Okay, now let us talk about something called the linear combination. So we can add and scalar multiply in the same equation. So we can do multiple scalar multiply, add, like it is done here. So this is like scalar multiplied with c1 on vector v1. Scalar multiply v2, vector v2 with scalar c2, scalar multiply vector vp with cp, and then you add it. Okay, so you add it, and this is called a linear combination of vectors. The vectors you were given were v1, v2, vp, and this is a linear combination of the vector. It's a combination, right? So that's why we call it and we call it linear because it's just a simple additions here. Okay, we are not squaring or whatever. Okay, we are not doing any nonlinear operation here. Okay, so v1, v2, v3 are in Rn and so on. So this is the formal definition of linear combination. We call W a linear combination of the vectors this. Okay, like it is done here. So it's already defined here, and the scalars this are called the weights or the coefficients. Okay, or in the combination. So we can think of linear. So let V be this and W be this. So what are some examples of linear combination these two vectors? Well, the simplest one is that I choose C1 to be 1 and C2 to be 1 and then add. So this is like 1 times V plus 1 times W. So this is like V plus W. Okay, so this is one linear combination. Okay, so similarly, we can have C to be 1 and C to be, so you can think of this as plus, and then C2 was -1. Okay, so by choosing the sign of C2, you can make it look like subtraction or addition. So here in this case, this is an example where this was like -1. C1 is 2, C2 is 0, C1 was 0, C2 is 2, okay, C1 is -1 and C2 is 0. So variety of combinations you can think of. C is a real number. So you can take C to be pi, C could be anything, rational, irrational number, whatever you want. Okay. There are some illustrations of this in the slides. I'm taking these slides from some prof, and he has built some nice illustrations also. So you can click on this and show some geometrical intuition also. Okay, so later on you can do that. Okay, so there is a Paul here. I mean, this is not really Paul right now, but it's just in the slide. So is there any vector in R2 that is not a linear combination of V and W? Okay, assuming that those vectors are like this. So let us say someone gives me two vectors, V and W. Now the question, the Paul that is asking is that let us pick any arbitrary vector, let us say here. Okay, so now the question is there any vector in R2? So this is R2, the plane. Okay, so this is the R2 plane, and we are given U and V and W exactly like in the figure. And we chose some vector which is here. Okay, so this is some vector we chose. And what we are asking is that is it possible that there will be some vector that is not a linear combination of V and W? Okay, so is it possible that some vector I will choose that can never be a linear combination of V and W, especially if the V and W are given like this? So what do you think? Right, so that's the question we are asking. What do you think in this example, in this particular example? Is it possible that there will exist one vector that can never be obtained as a linear combination of this?
Sir, if the vector comes out of the plane, that is the vector is in R cube.
Yeah.
There's not a linear combination of V and W.
Yeah, that's correct. So, but what I'm trying to ask is there any specific about this V and W that can allow you to represent any vector?
They are linearly linear.
So they are like linearly independent. Okay, I get the point. I have not defined the linear independence, but the fact that they make some angle, okay, that is crucial here. Some angle that is neither 0 degree or 180 degree. Okay, so geometrically you see that. Okay, so regardless of, to answer this, Paul, regardless of any vector you give me, since there is some angle given to me, I get that flexibility to come up with this this vector. Okay, I get the flexibility. For instance, in this specific example, the intuitive feeling I have is like to generate this vector, I will do some negative of W. So I will reverse the direction of W in whatever quantity I need, right? And then I will reverse the direction of V in whatever quantity I need. Okay. Okay. By whatever quantity I mean as much stretching in this direction, as much stretching in this direction for W, such that the sum will be actually this. Okay, such that if I move this guy doing vector addition, I do get this. So geometrically, you can get an intuition already that as far as some angle is there between the two vector, actually it's possible to generate by angle. I mean other than 0 and 180 degree. So 180 degree is still the same vector actually, essentially. I mean, it's just a reverse of that, right? Right. So, but these are considered to be like it's just the same combination, right? But if that is the case, then I can generate any vector. I only margin I need is something non-zero here, and then I'm done. So this is a geometrical thing that I can generate any vector as long as the angle between them, yeah, it's not really. Or a good way to say is that cosine of the angle, right? So it's like because at 0 like cos is 1, and at 180 the cos is 1, right? Or minus 1, right? So you can define some criteria when using cosine of the distance, angle, and so on, and then you can define when they are like they are aligning in the same direction or they are not. Okay, so that can be used to define the angle. So we will discuss that. So geometrically, I hope it's clear that any vector you give, as long as v and w are, so a correct way to say is that v and w are linearly independent. Okay, then they are making some angle other than 0. Okay, so that's the geometrical interpretation. So the answer to this, Paul, is that no. Okay, so answer is no. So these are more examples of linear combinations, and I don't think I have to discuss this too much. So what are the linear combination of V? These are the possible. What are all linear combination of V? Well, all linear combination of V will look like CV, where C you take any real number. Okay, so all scalar multiples of V. Okay, and this will form some line. Okay, because you are allowing all possible C, so this will stretch in either direction you think of, infinity, and this will go up to infinity. So that will form a line. So what are all the linear combinations of these guys? Like V and W, right? So again, you can play with this C times C1 times V plus C2 times W, and then you see what do you get from here. Now the question is, in this specific example, what are the possible linear combinations you are going to get? Okay, what are the possible linear, although there are like two vectors given to you, but if you do all possible linear combination, what type of vectors you are supposed to generate here? Okay, you see there is some pattern in the data here. So let us start with C1V plus C2W. What is this? That is the all possible linear combination, right? So in this case, C1V is like what? 2C1. Okay, this is the scalar multiplication, right? So 2C1 and 2C2, and then plus, and then this is what? Minus of C1. Okay, so sorry, C2 minus C2 and minus C2. So if you sum this up, okay, if you sum this up, what do you get? 2C1 minus C2 and 2C2 minus C2, right? So so what does this, like, what is this, right? Okay, I made a mistake here, right? Do you see that?
Sir, it's 2C1.
Yeah, I made a mistake of mixing these two. Okay, so let me do it again. Okay, so this is C1 is multiplying on the whole vector, right? So this is like 2C1 again, and this is like this is like minus C2 and minus C2. So overall, what is this? This is like 2C1 minus C2, and this is like 2C1 minus C2, and this is like same thing as saying, so let us say these numbers are C3. This is like same thing as saying C3 times 1, 1. Okay, and C3 is defined to be 2C1 minus C2. So this is yet another scalar that multiplies to 1, 1. So you see, if you take all possible linear combination, what you end up in the end is nothing but just a scalar multiple of 1, 1 vector itself. Okay, so you will make it into a line only, although you have given two vectors, and if they were linearly independent, in this case they are not, because V is because V is minus 2 times W. So hence they are dependent because I can obtain one from the other by some suitable. So in this case, although two vectors are there, all possible linear combination just gives me a line. Okay, if they were independent, I could have filled the whole space, because in the previous slide I told you that if they make even a slightest of the angles other than 0 and 180, then like I can produce any arbitrary vector. In other words, I can fill the whole space. Okay, so let us look into vector equations and the span. Okay, so let us consider systems of linear equations. These things show up a lot. Even in while solving the optimization problem, you will see that sometimes you are led to solving some linear system. So this is a simultaneous system of linear equations, and you have x minus y is 8 and so on. Okay, so we can write all three equations at once as a vector. So we could have also written this as a vector. But important thing to understand is that we can also write this as a linear combination. Okay, so we can write this as x times, because this is here and this is here. So we could have written this as x times 1 to 6, and this we write this as y times minus 1 minus 2 minus 1, like it is done here. So we could write this as a linear combination, right? So solving a linear system means what now, right? How do you interpret this in terms of this? So someone asks you to solve this, but in terms of vectors and linear combination, what you are asking for is which linear combination of 1 to 6 minus 1 minus 2 and minus 1 will lead me this. Okay, will lead me to this. Okay, in other words, what we are asking for is some vectors are given to us. Let us say 1 2 6 is this, and let us say this is minus 1 minus 2 minus 1. I know that is wrong, minus 1 should be here, but doesn't worry. And someone gave you a vector 8 16 3. Okay, and solving a linear system is like asking whether I can do whether some linear combination of these vectors can give me this vector, which is somewhere here. Okay, so let us say this vector is somewhere here. So it's the same thing as asking, is it possible to have a linear combination of the given vectors to arrive at the right hand side? Okay, so this is a different view, which is a very important view actually in linear algebra. You see solving linear systems as a problem of a linear combination. Okay, so same thing. So this is the question that we are asking: is 8 16 3? Someone gives you a linear system, then this is what you may ask in an alternate way: is 8 16 3 a linear combination of these two guys? Okay. So or other way is like, what are the scalar multiples of these? Okay, which is the solution to the linear system? What are the scalar multiples which will actually lead us to this, right? Okay. So I don't think I need all of these here in the slide, but I can go through this quickly. I will follow only the essential parts, not really everything. So one way to solve, if you recall from linear algebra, is that I can write this in matrix form. So this coefficients here can be written here, and then this is the right hand side. And then we do something called row reduction. Okay, if you've forgotten, it's fine. We don't need these things in this course. Okay, only concepts of linear algebra we need. Solve part can be done using some library. Okay, the focus here is on optimization. Okay, okay. So we can do something called row reduced echelon form. Row reduced echelon form in very short form is like you do certain number of row operations, subtract let us say second row from the 2 times of the first row, then it will become 0 and these guys will change, and then you also make this guy 0. Okay, then you move here and then you do some subtraction also again using previous rows and so on. and then you using this, let us say you make this 0 and so on, and then you divide some rows by some constant, so that you do all these operations so that the leading entry of each row becomes 1, and the leading entry of second row starts at the second place. Okay, and so on. Because if there was anything, I could have made it 0 using this. Okay, so that it is possible. That's what I'm trying to say. So this is called a row reduced form, where the leading entry of this is 0, and then the leading entry of the second row cannot be on the same column. Okay, it has to be 0. It can be always made 0. Now this can be 0, but any leading entry that is coming, let us say it should be 1. But the next row that is going to follow, leading entry must be after the leading entry of this. So it must be here. Okay. If not, then like I could have flipped also, right? So I could have flipped this. If there was 1 here, then I could have permuted, because permutation is also allowed of the row. So it is possible to make this look something like this. Okay. And this is called elementary form. And here you have the right hand side reduced. Okay. The reason why you do this is that it's easy to solve after that, because once you have this, from there you can read out, because the variables are here, right? So y will be -9 and x, because that didn't change. Okay, so this system now boils down to 1 0 0 1 x y and -1 -9. Okay. So this is like the usual, you see in the high school you used to do subtract, eliminate variables. This is exactly what is done here. It's just that we are working, because x and y doesn't change during subtraction. So that's why we removed that, and we did all those subtraction, divide, whatever equations and so on, and we arrived at that so that we can easily solve after eliminating the variable. So this is called row reduced echelon form, and that is used to solve the linear system. We can automate this. We can make it an algorithm. In some cases, you may not have solution also. That may happen, but we can automate these things. Okay, because in some cases you may end up something like this: 0 0, and then something is here 4. Okay, this is not. I mean, this is absurd, right? So 0 0 cannot be become 4. So it can happen things like that. So then you can in those cases you will say no solution. Okay. So so from here you could find x and y, and then we can answer that. Okay, the linear combination that we were looking for, that indeed solves our linear equation, is -1 of the first vector, -9 of the second vector, and that is the right hand side. If we can find a linear combination like that, then we call it to be a consistent linear system. So consistent linear system are the systems that has a solution. Okay, and we have found a very important relationship between the vectors in the linear combination, the matrix form of the linear equations. Okay, so the vector equations like this. So when someone asks you for a given b, is there a linear combination of the vectors v1 to vp such that I get b? Then your answer should be is the same thing as saying whether I have a solution to the linear system a times x is equal to b, where a is this v1 column stacked like this. Okay, and x is the vector x1, x2, xp. So now and b is also a vector. Let us say b is like b1, b2, bp. So what you are really asking for is ax equals to b. Okay, so the question of asking whether b is a linear combination of v1 to vp is the same thing as asking whether there exists a solution to the linear system ax equals to b. Okay, so that's what we are asking here. Okay. So it is important to know that all linear combinations of a set of vectors is this, and it's exactly the collection of all b. Okay, so all linear combination is nothing but the set of all these vectors b, and and it has a solution also. Okay, so all linear combination are those for which Ax equals to B has a solution. So you keep changing the B. Let us say I change the B to some other. Let us say I change the B to some right hand side to C. Okay, so for this C, if I don't have a solution to this, then this linear combination can never produce C. The linear combination of these vectors Vi can never produce C. In other words, there is no solution to this linear system. Okay, so let V1, V2, Vp be the vectors in Rn. The span of V1 to Vp is called a collection of all linear combination of V1 to Vp and is denoted by this. So you take this vector V1 to Vp and take all possible linear combinations. Okay, and that is called the span. So we can define the set like this: is the set of all linear combinations. It's all because I am varying x1 to xp arbitrarily in the real number. Okay, other synonym for this is like the span V1 to Vp is the subset spanned by or generated by V1 to Vp. We can also say that this is generated by V1 to Vp because I'm using V1 to Vp and then I'm taking linear combination out of that to generate new vectors. Okay, so so this is the, so I can stop with this slide. If we don't stop, otherwise the videos get split. So let us see. So now we have several equivalent ways of making the same statement like we did before. A vector B is in the span of this. This is the first statement. Then this means, so all three are equivalent. Okay, so vector B, we say in text verbally, vector B is in the span of V1 to Vp. This is the same thing as saying that this vector equation has a solution. This is the same thing as saying that Ax equals to B has a solution. Okay, so this is like Ax equals to B has a solution. You will do the row reduced echelon form and so on to identify whether you indeed got a solution or you got some inconsistent thing. Okay, so you can go and look into the interactive examples where it will show you when the linear systems are called inconsistent and so on. So this is where I will stop. And as I said, I might do this review in the second class, but I will take some extra class to compensate for the loss in the classes for the optimization. Okay, so I will see you in the next class. There will be tutorials. I hope all of you participate in the tutorial because your participation and the poll results will tell us what is the suitable time for the what is the suitable time for the tutorials. Okay, so